So now in this video, we're going to look at the voltage across the load in this case, which is either going to be an LED or a switch. We're going to look at that coming up for a NOT gate. So you can see here we have a switch. You have to push the button to turn this switch on, this push button switch. And the LED is on though. And so the switch is off, but the LED is on. These top two pins are always connected. Current can go through the resistor and then through the LED. Make sure the long lead heads towards more positive, short lead more negative, long lead anode, short lead cathode. But in case, there you can see I press the button and now the LED is off. I don't press the button, the LED is on. So the main thing is parallel components, I'm back kind of farther, have the same voltage across them. That is the basic principle right there. And so when a switch is open and parallel to an LED in this case, it has basically infinite resistance. It's as if it doesn't exist. For the most part, current flows through freely. So I'm using 5 volts at the moment and a 1 kilo ohm, 1000 ohm resistor over there. That's why the LED is not very bright. So we're going to look at that voltage coming up, and we're going to get the forward voltage of the diode. Well, the button is not pressed. When we press the button, we're going to see that as we press the button, the LED is going to go out. That's because there's no voltage across it. We have a direct connection. That's all one node, basically one solid piece of wire all along there. So any current that goes through there has nowhere near the voltage, practically zero, to get the LED to conduct. It's probably going to take about 1.5 or 2.5 volts at a minimum. And so it's a direct connection. So both sides of the LED are directly to ground. That's a 0 volt difference. It does not light up. So now I got my pocket oscilloscope right there, and each square across is 1 second. Each square up is 1 volt. It's down at 0 right now because we have the alligator clips here clipped to these jumpers, not connected to anything but blank rows. So we're going to put this one to that spot. We could also put it to that spot. It's a direct connection. Doesn't matter right there. We could even put it over here. It will work just fine. We'll look at that. I'll come up here and we're going to go to the long lead of the LED. You can already see I bumped it and we got some voltage. But there we go. So that's 2 volts. That's the voltage that the LED is blocking while it is forward biased. It's forward voltage. 2 volts. We're dealing with 5 volts at the supply. We're getting about 2 milliamps of current right there, approximately. It's probably actually 3 milliamps, but it's about a milliamp off because that's a 1 kilo ohm resistor. If that's blocking 2 volts, then we will have 3 volts across this resistor, which again, we can look at. We'll just go up there and then go across the resistor, and then you can see 3 volts. So it's actually probably 3 milliamps of current, but we're not being too picky right now. Now, we'll put those back. We got the 2 volts for the red LED. I'm going to grab the green LED, and again, this is a bit unusual for my videos, but negative is higher up than positive for the LED. So long lead, the anode is down 1 row, short lead, the cathode up 1 row. It's a green LED. It's a lot brighter, but it has more voltage across it. That's not why it's brighter. It's just naturally brighter. It has more voltage. What is setting the current is the resistor again. So we'll look at that voltage. This is a video about voltages. And there you can see we have a little more than 2 volts right there. And the power supply, although it's not accurate, it's clearly lower current than it was before. So that's the main takeaway. But in any case, now we're going to look at what we originally looked at. We've done those voltages in other videos, but still a good idea to do them again for review. There we go. We got about 3 volts across the LED. It's lit. That's what it takes to get it to conduct, and then it starts conducting pretty freely after that. The resistor sets the current after that point based on the voltage it gets there. I press the button. Now there was no voltage when I pressed the button. So we got a short circuit. When I close the switch, the bottom and the top connect directly together. They connect directly to ground. We have ground on both sides of the green LED. And of course, if we do the red LED, we have the exact same thing. Again, you got to make sure it's in the right way. It's backwards from what it normally is. But there you can see 2 volts across the LED. Well, the button is off, the LED is on. When I turn the button on, the LED is off. So it's a simple NOT gate. It wastes current though. We'll zoom back here. You can see we got about 3 milliamps. Now it looks more accurate. When I press the button, now it's 4 milliamps. So we actually have more current flowing when the LED is off. So it's not energy efficient. It's better to use a NOT gate integrated circuit. But you see similar circuits to this out there. So knowing how this works will help you understand those when it comes to voltages. So thanks for watching. Make sure you check out one of the other videos. Click like, subscribe, the bell, and all that. Donate to Patreon if you can. I have a bunch of links in the description. That would help out a ton. I will see you in the next video.